Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And once again, this hour is your hour. Okay, well, let's move right along and take the first listener question.
Hello, Dr. Kaku. This is Juan from Atlanta, Georgia. I'm listening online through Stitcher. My question pertains to Einstein's theory of gravity. I was wondering if the moon contributes to the overall gravity of the Earth, and likewise, without the Earth, would the moon's gravity be different? Thanks. That's my question. Look forward to your answer. Bye.
Okay, well, the moon has its own independent gravity as well as the Earth. According to Isaac Newton, every particle of nature, no matter how small, has a little bit of gravity, and when you add it all together to create something like the Earth, you can get a large gravitational field. So even though the moon has its own gravity, its gravitational pull affects the Earth in terms of tides. And so the fact that we have tides is due to the fact that the moon literally lifts ocean water up. Even though the moon is about 250,000 miles away, we feel the effects of the tides on the Earth. And the Earth, in turn, affects the tides on the moon. Now, the moon, of course, has no water, but what rises on the moon is rock. So even though the moon seems to be spherical, actually it's not. It's slightly football-shaped. And it turns out that the stable orbit of a football around the Earth is to have one side of the football face the Earth at all times. Now, have you ever noticed that you've never seen the backside of the moon? I mean, think about that for a moment. Stop. Have you ever seen the backside of the moon? And you begin to realize that, yeah, most people have never seen the backside of the moon. Think of the moon. It's the same moon that you saw as a child. It's the same moon you see on TV specials. It's the same moon you're going to see tonight, the same face of the moon. One side always faces the Earth. Why is that? Tidal forces. Tidal forces lock the moon in a way such that only one side faces the Earth at any given time. The only time you will ever see the backside of the moon is in a special on television where they actually show satellite photographs of the backside of the moon. And speaking about tides, let me say something else. It turns out that the moon is leaving us. That's right. Every revolution, the moon gets a tiny bit farther away from the Earth than us. This you can actually calculate numerically using, again, Newton's laws of gravity. You can actually calculate the fact that the moon is leaving us. Now, this was known to astronomers over 100 years ago. In fact, some astronomers said the following: if the moon is leaving us at a known rate, then let's run the videotape backwards. If you run the videotape backwards, that means that in the past, the moon was much closer to the Earth than today. And then if you run the videotape all the way back, you realize, oh my God, the moon came from the Earth. The moon is leaving us slightly, few inches a year, I think it is, very slightly, but over billions of years, that adds up. And yeah, billions of years ago, the moon was much closer to the Earth. In fact, it came out of the Earth, roughly 4.1 billion years ago. So yes, to answer your question, the gravity of the moon is distinct from the gravity of the Earth. However, the two influence each other by something called tidal forces. Oh, by the way, before I leave on this question, let me say that this is also the reason why Saturn has rings. The distance of the rings of Saturn from the center of Saturn is called Roche's limit. Why is that important? Because you can calculate numerically, using Newton's laws of gravity, that if a moon gets too close to the mother planet, tidal forces become so great that the football gets squeezed more and more into a sausage, and then it falls apart. The distance at which a moon will fall apart if it gets too close is called Roche's limit. And bingo! That's exactly where we see the rings of Saturn. So the rings of Saturn, yes, are a byproduct of gravity, In turn, you can calculate all these effects using Newton's laws of gravity. Okay, let's take a short commercial break. Once again, you are listening to Science Fantastic.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, moving right along, let's take the next listener phone call.
Hello, Dr. Kaku. This is Mustafa from Kansas City, Missouri. The station's name is KRMS. It's always a pleasure to listen to you, Dr. Kaku. So my question is about energy of a photon. Since all wavelengths of electromagnetic radiation moves at the same speed and light is a visible spectrum of it, why does a higher frequency photon have more energy? Thank you.
Okay, well, you ask a question that goes right to something called the quantum theory. And the quantum theory is not just a sexy term that you use at a cocktail party to impress your friends, but the quantum theory is really the basis of reality itself. And it all starts with that simple question that you just asked. And that is, what is the energy of a photon? Well, let's break it down. First of all, what is a photon? On Star Trek, Captain Kirk says, man the photon torpedoes. Well, a photon is a particle of light, a tiny particle of light. So what is a photon torpedo? A flashlight. A flashlight is a photon torpedo because it shoots trillions upon trillions of photons. And so photons are the basis of light. Now, it also vibrates, which is another aspect of the quantum theory. The first postulate of the quantum theory says that energy occurs in packets. These packets are called quanta, and that's where the name comes from. Quanta is a packet of energy called the photon. Now, each packet of energy, in turn, vibrates, okay? And it vibrates at a frequency. Low-frequency vibrations, for example, would be something like radar, microwaves, radio, television. They would be low-frequency vibrations. When you increase the vibrations, you get into light, colored light. Roy G. Biv, that is red, orange, yellow, blue, indigo, violet, the colors you learned when you were in elementary school. These are the frequencies associated with visible light. But then it goes on. Then you have frequencies that are higher than visible light, like X-rays and gamma rays and ultraviolet light. Now, if you listen to what I just said, you realize that there's a pattern there. Ultraviolet light, X-rays, gamma rays are dangerous. They cause cancer. They cause sunburns. They are the energy source of the atomic bomb itself. They are the energy that comes out of the sun, which can give you a sunburn. So in other words, the higher the frequency, the more the energy. On the other hand, if you put your hand in front of a television set, you don't feel anything at all. And that means that television waves are not harmful at all. They're non-ionizing. That is, they don't rip the atoms apart. So you realize there's a pattern here. Higher the frequency, higher the energy. The man who first figured that out was a guy named Max Planck in 1900, and that gave birth to what is called the quantum theory. And the quantum theory, in turn, what does it mean to you? And the answer is everything. All the appliances you see in your household, all the gadgets, all the wizardry, the internet, everything is a consequence of the quantum theory. Now, you ask yet another question that is more difficult to answer, and you ask the question, why is that so? Well, we don't know. We just know that the higher the frequency, the higher the energy. In fact, there's a formula for it that every grad student in physics has to learn. Energy equals a constant times the frequency. Higher the frequency, higher the energy. That's why X-rays are dangerous. That's why ultraviolet light, gamma rays are dangerous. Gamma rays, for example, come out of nuclear detonations. Very dangerous. And on the other hand, that's why infrared light, That's why television, radio are not so dangerous. They have much lower frequency, therefore lower amount of light. And if you want to know more about the quantum theory, get a copy of one of my earlier books, Parallel Worlds. And again, why is the quantum theory so controversial? If there's so much evidence, a preponderance of evidence concerning the correctness of the quantum theory, how come it's controversial? Well, it's controversial because, well, Einstein himself had severe reservations about the quantum theory. He once said famously that the more he learns about the quantum theory, the sillier it gets. Now, he meant by that you don't really know where the photon is at any given point. In other words, the photon can be two places at the same time. Now, at that point, Einstein drew the line. He said, "Ha! This is preposterous. I mean, come on, give me a break. An electron or a photon can be two places at the same time." Well, yeah. In fact, that's called modern electronics. If the electron could not exist in two places at the same time, we wouldn't have any electronics at all. Now, let's say you don't buy that. Einstein certainly didn't buy it. What do you do about it? Well, tough luck, kid. I mean, the quantum theory is correct. Modern civilization is based on the quantum theory. Lasers, transistors, computers, all of it from quantum theory.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, let's move right along and take the next listener phone call.
This is for the epitome of a great scientist. My name is John Hay, and I'm curious as to the best starter telescope for 6- and 7-year-olds. I want to get them involved, as I know no one who has the expertise that you might. Thank you.
Okay, well, you asked a question about 6- and 7-year-olds, and let me say something, that when we're very, very young, we're born scientists. All of us want to know where we came from, why the stars shine. We're born scientists, and that's the time when you want to grab them. That's the time when you want to show them the incredible universe of ours. In other words, around, let's say, even age of 10, that's when they can really appreciate it. That's when you give them a telescope, a microscope, a chemistry kit, a visit to the planetarium, and you blow their mind away. That's when it starts. Until, of course, you hit junior high school, and then it's all over. Junior high school, I think, is perhaps the greatest destroyer of scientists known to science. We lose scientists by the millions every year once they hit junior high school. And why is that? Because science becomes boring. Science becomes memorization of irrelevant facts that don't mean anything at all. And if you're a science buff, you're called a geek. And you learn there's a pyramid. At the top of the pyramid, if you watch Hollywood movies, you know the top of the pyramid are the beautiful people. That is, the cheerleaders and the football jocks, they are at the top, the pinnacle of the pyramid in high school. And who's at the bottom of the pyramid? Everybody else and the nerds. But they don't tell you that. They don't tell you the fact that once you graduate from high school, the pyramid turns upside down. I mean, just look at who the richest people in the world are. People like Mr. Zuckerberg, Mr. Gates. I mean, think about it. We're brainwashed, and it's no wonder that we lose young scientists. Anyway, then what do you give a young person? I would first give them a pair of binoculars. Why is that? Because telescopes, well, you don't want to spend hundreds, thousands of dollars on a telescope only to find that your kid loses interest. First, give them a pair of binoculars and show them what you can do with it. Then you can magnify images and open up a whole new world to them. And go on parties where you go out at night and look at the craters of the moon. Look at the rings of Saturn. You'd be surprised that, yeah, even a small telescope, you can barely make out the rings of Saturn. I first remember when I saw the rings of Saturn, it literally blows your mind away. There's a universe out there. Rings of Saturn, visible with a good pair of binoculars. Once the kids are hooked, once the kids say, okay, Dad, okay, let's go to the next level, then you may want to look at the different kinds of telescopes there are, and there are basically two kinds of telescopes. One is the telescopes called refracting telescopes that look like a spyglass, a long tube. The other one is the reflector, which is basically a light box. It looks like a barrel, and you poke your eye on the side of the barrel. Light comes in the barrel, is collected, and then a mirror shoots it into your eyepiece. Which is better? Well, I personally think that the reflecting telescope, first devised by Isaac Newton himself, is preferable if kids start to become more serious, like a 4-inch reflector. But again, first test them out of binoculars and tease them and see whether they're really interested. If they are, then hey, go for it. Because who knows? Maybe you have a scientist budding right before your eyes. And remember, the job market for science is great. Okay, well, let's take another short commercial break. You are listening to Science Fantastic.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, let's get right to the next listener phone call.
Hello, this is Saul Yang calling from Oklahoma. I heard your station online, and my question is, you mentioned that the moon came from the Earth. So if the moon or a piece of an asteroid hit the Earth and then turn into the moon, how come the Earth is still in orbit with the other 8 planets? Will that cause the Earth to be out of orbit? Thank you, and looking forward to hearing from you.
Okay, well, the dynamics of the moon have fascinated astronomers for, of course, hundreds of years, but it's only been within the last century that we've been able to nail down the details. First of all, the moon is leaving us a few inches a year, and as a consequence, if you run the videotape backwards, you begin to realize that the moon must have come from the Earth. But that's just a general statement, that if the moon is leaving us, then in the past, perhaps it came out of the Earth about 4 billion years ago. We want more concrete evidence of this, and that comes from the space program. When our astronauts landed on the moon, they were able to get moon rocks, lots of moon rocks, and bring the moon rocks back to the planet Earth. And scientists were shocked when they actually analyzed the moon rocks. First of all, they found the chemical composition of moon rocks is almost identical to that of the planet Earth. Now, why is that so shocking? That's shocking because asteroids are quite different in their chemical composition from the Earth. We have iron meteorites, we have carbonaceous meteorites, zinc and what have you, chemicals that we can analyze, and the chemical composition of moon rocks was quite different, quite similar to the chemical composition of the Earth, while asteroids are quite different. And so that led us to believe that, yes, the moon came out of the Earth, perhaps 4.1 billion years ago, an object the size of Mars plowed into the Earth, but did not cause enough perturbation to send us into the sun or anything. It was a glancing blow, and so it did not affect the overall stability of the give us a call. Okay, well, let's move right along and take the next listener phone call.
Hello, Mr. Kaku. This is Lawrence Kim from Louisville, Kentucky. I usually listen to you on the podcast. Most recently, it was in NASA saying that they're testing the EM drive, and it was starting to break the laws of physics as far as Newton's second law. I'm not too familiar on how that's breaking the law or if it even is. I would love for you to elaborate on it. Thank you.
Okay, yes, I've been getting quite a bit of emails ever since publication tried to give a little bit of credibility to what is called the EM drive. Personally, I am a skeptic, but let me explain what's happening. First of all, our chemical rockets have pretty much reached the limit of their efficiency. Chemical rockets simply cannot take us to the stars. It would take 70,000 years for a Saturn rocket to reach the nearest star. And we can't wait 70,000 years to reach the stars. And so engineers and physicists have been frustrated. We've looked at other designs. One popular design is the laser rocket, riding on a laser beam. Light itself has pressure, and you can use the power of a gigantic bank of laser beams to energize, let's say, a sail. And that's one way to do it. Another way to do it is to use radar of some sort. This is the electromagnetic rocket that you mentioned. Now, electromagnetic radiation has pressure. That's why we have the possibility of laser rockets. Very small, but possible. Some people have said that why not build a chamber, shoot radar inside the chamber, and just like a rocket, one side is open, and the radar shoots out one end, and the rocket goes to the other end. Well, it sounds great, but then you do the math. You do the math, and you find out it's much too small, that you're not going to get much thrust at all using radar or something like radar. However, that hasn't stopped some people from dreaming about the electromagnetic rocket, and there was an article that was published that has generated a certain amount of interest because maybe there's an experiment which can show that you can indeed obtain usable thrust using the electromagnetic rocket. Now, why am I a little bit skeptical? Because when you do the math, you realize that, well, you can't get something from nothing, that if you have this electromagnetic rocket, you can calculate the thrust. The thrust is simply too tiny to energize a starship, so this result must have been incorrect. Now, am I positive about this? And the answer is no. I have not seen the paper. I have not done I have not observed the experiment, and so in some sense I have to be open to all possibilities. Scientists are what we call revolutionary conservatives. That is, in general, we're very conservative when it comes to breaking the known laws of physics, but if someone can successfully break a law of physics, a law of Newton, a law of Einstein, we're radicals. We accept it immediately because we realize, hey, Mother Nature is telling us something. But as Carl Sagan once said, remarkable claims require remarkable proof. And already some scientists are jumping on this idea and saying that, well, perhaps it's been overhyped. Perhaps the physics is simply not there. But hey, like I said, I keep an open mind, and I think the experiment has to be redone, and the critics will have their last say. For example, some people email me, in fact, quite a few people email me, and ask me about cold fusion. Well, cold fusion is getting energy, fusion energy, the energy of stars, in fact, out of a bottle, a glass of water containing some rods of palladium. Now, if you do, again, the math of quantum mechanics, you realize that you're simply not going to get energy from a glass of water that harnesses the energy of the stars. However, the people who believe in cold fusion say, ha, you guys are prejudiced. Obviously, you don't believe in the results of real experiments, which seem to indicate that you can get energy almost from nothing. Well, it turns out that these experiments are not reproducible on demand. That is, some inventor on one part of the earth says, I got it. I got cold fusion in a bottle. But another group tries to duplicate that very same experiment, and nope, nothing happens at all. Now, science is based on things which are reproducible, testable, and falsifiable. And that's the weak spot of cold fusion. hey, maybe a law of physics can be violated. That'd be great. There's a Nobel Prize waiting for the person who can prove that. But, well, remarkable claims require remarkable proof. And at the present time, nobody has created a reproducible cold fusion engine. Toyota, in fact, spent, I think, over $1 million trying to harness this and gave up. So the proof is
now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, without further ado, let's jump right into some of the listener phone calls that have been pouring in.
Hi, Dr. Kaku. This is Andrew Call here, and I just wanted to know if it was possible that we could have misinterpreted the results of the Michelson-Morley experiment. Let me know. Thanks. Bye.
Well, the short answer is no, but let me answer the question in more detail. In the 1900s, physics had this tremendous crisis. People were wondering that if light is a wave, then what is waving? That's a question that even children could ask. If light is a wave, then what is waving? And so scientists came up with this ethereal quantity called ether. Ether fills up the universe and is an absolute frame, so you know exactly where you are with respect to the stationary universe. So ether was this absolute frame of reference. Then we had the Michelson-Morley experiment, they shot light in two separate directions and calculated the relative speed differential if light goes in two different directions perpendicular to each other. And much to their shock, and the shock of the entire physics community, light traveled at the same velocity no matter which way it was going. Now, think about that for a moment. If you have a light beam and you shine a flashlight in the forward direction, or in the horizontal direction, vertical direction, or to the ground, you expect the speed of light to be different. If you're on a train, you expect the speed of light to be different if you shine a light in the forward direction. In fact, if the train is traveling near the speed of light, and you turn on a flashlight in the forward direction, you expect that flashlight to go twice the speed of light. Well, the answer was all of the above are wrong. This was a shock wave. That no matter where you point the flashlight, light travels at the same speed, whether you're in a rocket ship, whether you're going north, south, east, west, diagonal. The universe didn't care. The speed of light was a constant no matter where you went. And therefore, it was Albert Einstein who finally figured it out. And that is that in order for light to travel at the same velocity in any direction, up, down, sideways, whatever, it meant that time itself has to be distorted. Time slows down the faster you move. And in fact, the GPS system depends upon that because we have to know what time it is in outer space. Duh. I mean, the astronauts can't go into outer space and not know what time it is. They have to know what time it is. But time moves at different rates throughout the universe. Time slows down for the astronauts. In fact, the astronauts are shifted in time by a few millionths of a second when they go up in outer space, a tiny, tiny amount. Also, time beats faster on the moon than on the Earth, all of which can be measured. Now, some people say, well, isn't relativity a theory? Therefore, it's not really proven, right? Wrong. Relativity is a law. It's not a theory at all. That's a problem with the English language. It is a law. Just like we have Newton's laws of motion, Einstein's laws are actually more powerful than Newton's laws of motion. And so the Michelson-Morley experiment showed that light travels the same no matter where you point the flashlight. And the only way to explain that incredible fact is to assume that time and space can change depending upon how fast you move. And we measure this. In fact, the Pentagon cannot fight wars unless the GPS system is calibrated to take into account relativity. And the space program will be thrown completely out of kilter unless we realize that the question, what time is it in outer space, depends on how fast you move, and it depends on where you are. As I said, time beats faster on the moon than it does on the Earth. And if you don't like it, tough. That's just the way the universe is. If you think that, well, doesn't this violate common sense? Well, tough. The universe doesn't care about your common sense.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, moving right along, let's take the next listener phone call.
Just wondering in what ways we are measuring the impact of the methane bomb in the Arctic. You know, are we monitoring those large stores of underground frozen methane? And, you know, what is the potential for that to be disastrous or lead to runaway climate change in this century? I wish you could provide us information on that, because it's very hard to find information on that. Thank you.
Well, you ask a very important question, and that is, well, the Arctic is gradually thawing out. We know this for a fact. Even people who don't believe in climate change will acknowledge the fact that, yes, satellite data shows that the Arctic is warming up. For example, submarines that went underneath the ice caps in the 1950s, like the Nautilus, measured the thickness of the ice cap. We've since been there many times since then, and we find that the thickness of the Arctic ice sheet has gone down by 50%. Just in the last 50 years. I mean, think about that. In the last 50 years, we've lost 50% of the thickness of the ice sheet. In fact, in summer times, we now believe that the Arctic will be more or less ice-free in the coming decades. And the Russians are even depending upon this. The Russians have made very distinct claims that, yes, when the Arctic thaws out, they want to be there to claim part of it. In fact, I had a chance to lecture in Russia several years ago. I spoke in Siberia, of all places. I spoke in Krasnoyarsk in Siberia. And the people there say that, well, winters used to be brutal. I mean, really brutal in Siberia in the winter times. But hey, because of global warming, the Arctic is gradually thawing out, and they love it. Yes, some people actually love climate change, especially if you're ice-locked in Siberia. And when I went there in summertime, it was actually rather pleasant because of the fact that the Earth is heating up. And they also mentioned to me that because the Arctic is gradually thawing out, it means that mammoths and animals, prehistoric animals that died tens of thousands of years ago, are now coming out of the ice. So this is sort of like a Hollywood movie, The Revenge of Prehistoric Monsters. Because the Arctic ice is gradually thawing out, it means that we're beginning to pick up the carcasses of animals that died tens of thousands of years ago, like the woolly mammoth. Now, the question that was posed is about methane gas. Methane gas is a byproduct of the decay of organic materials. And if the Arctic ice is gradually melting, it means that, yes, the tundra is also melting. In fact, you don't have to go to Siberia, just go to Alaska, and you'll see the effect of the fact that the permafrost, the so-called permafrost that we consider to be frozen solid underground, parts of it are thawing out. And as the tundra begins to thaw out, it releases methane gas, and methane in turn is 20 times more potent than carbon dioxide in terms of causing climate change. So there's a potential of a runaway effect. Now, we should point out that this runaway effect is not going to happen anytime soon, so we don't want people to become hysterical and panic. However, it is something that has to be monitored very carefully by satellites and by climatologists in these various areas. The warmer it gets, that means more tundra is exposed. The more tundra is exposed, the more methane gas goes into the atmosphere. And the more methane gas goes into the atmosphere, it means that global warming accelerates, because methane is much more potent as a climate change gas than carbon dioxide, and then the cycle repeats itself. So again, there's no cause for immediate panic. In fact, the Russians in some sense are depending upon this so that they're not going to be so landlocked, and they're going to have access to warm water ports. And this is something that the czars of Russia wished for hundreds of years ago. And that's one reason why St. Petersburg, in fact, was created out of marshland by Ivan the Great in order to get access to warm water ports and trade with the West. And so then the questioner asked another question. How dangerous is this? Well, it is potentially very dangerous because we're messing around with the atmosphere of the planet Earth. However, it's not a problem that's going to peak in this generation, but it's a problem that our children and our grandchildren are definitely going to have to face. And again, you don't even have to believe that human activity is generating climate change. We know that the climate change process, whatever caused it, is in effect. And it could reach a point where it becomes autocatalytic. That is, it feeds on itself, and you get a chain reaction. We're not there yet, but again, the Russians seem to welcome this possibility. Most of us fear this possibility. Okay, well, let's take the next listener phone call.
Why do you call the string theory a theory if it cannot physically be proven?
Well, you ask a very embarrassing question, but a very fair question, and that is that sometimes great theories are proposed, but a test, a knockout test of the theory could take decades. And that's the way it is with all sciences. For example, when the theory of continental drift came out, it was laughed at for decades. In fact, I remember as a kid in elementary school, it was pointed out that, gee, doesn't Africa look like Latin America if you put the two continents together? The elementary school teacher actually laughed and said, ha, that's just a theory that's obviously incorrect. How can a continent move? I mean, continents are huge objects. How can you move a continent? But the elementary school teacher was fair and said that, yes, it is a theory. It's a theory that cannot be proven and probably is incorrect. Well, now we know that that is, of course, the guiding principle behind all of geology. Just like evolution is the unifying principle of all life and DNA on the Earth, continental drift is the unifying principle of all geology. But it took decades to actually prove it. In fact, it wasn't until we had submarines that could go down to the bottom of the Atlantic Ocean and photograph new volcanic materials coming out of a crack in the Atlantic Ocean that it was finally, quote, proven that we can actually see continents move. Continents move at the rate at which your fingernails grow, about an inch every few months, and we know that it's true. Well, after the break, let's take a short commercial break, but afterwards we'll talk about string theory and how we might eventually be able to prove it.
You're listening to Science Fantastic with Professor Michio Kaku. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, in this hour, we're throwing the lines open because this hour is your hour. Okay, well, moving right along, let's take the next listener phone call.
Hi, this is Brady calling from Denton, Texas. I'm a big fan. I'm kind of at today for the moment and hoping to change that. And I was kind of curious as to, and if you could possibly give an explanation, how scientists are able to entangle particles in the lab and how this process occurs without scientists, like in nature and the universe. Thank you.
Okay, well, you ask a question that is at the cutting edge of computer research, and one day your computer may depend upon this concept called entanglement. Well, first of all, we have a theory of atomic physics. It's called quantum mechanics. We see no deviation whatsoever from the laws of quantum mechanics, and it's what I do for a living. And in quantum mechanics, all matter is a wave. All matter has wave-like properties. And when you have two electrons that are very close together, in fact touching each other, they vibrate in unison. They go up and down, up and down. They vibrate in unison. Now separate them. When you separate these two electrons, then there is an umbilical cord. An umbilical cord you cannot see, which mysteriously connects one with the other. Einstein hated this. Einstein himself did not really believe in quantum mechanics, but hey, what can I say? He was wrong on this question. And this entanglement, therefore, means that if you jiggle one electron, then there is this mysterious umbilical cord connecting it to its twin, and it understands the fact that its partner has been jiggled. This experiment has been done. It was first proposed in 1935 by Einstein himself. In fact, Einstein created this experiment, this mind experiment, in order to disprove quantum mechanics. He said that any vibration of one electron would immediately spread to the other electron by this umbilical cord, and it would travel faster than the speed of light, and bingo. It says nothing can go faster than the speed of light. Quantum mechanics is wrong. So Einstein thought he had it. Einstein thought that he had the fatal plunger that would then kill off quantum mechanics. Well, this experiment has been done. We do it every day in our physics laboratories. And what can I say? Einstein was wrong. There really is this umbilical cord. It's called spooky action at a distance. These are Einstein's words. And he invented these words, of course, to try to smash it. But instead, hey, Mother Nature is what Mother Nature is. And it turns out that Einstein was wrong. Then the next question is, can you use this, as many science fiction writers have proposed, to send a message faster than the speed of light? If this information travels instantly, then does it violate relativity? We'll answer that after the break.
This is Science Fantastic. Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. We're throwing the lines open because this hour is your hour. Okay, well, let's get right back and take the next listener phone call.
Hi, Dr. Michio Kaku. This is Aiden Cumming-Teicher, and my question is, what number one advice would you give to a young entrepreneur who wants to become a quantum physicist? Thank you.
Wow. Well, that's a tough question, but I think your question is in two parts. First of all, to become a quantum physicist, and second of all, to become an entrepreneur. So let's try to break this down. First of all, if you want to become a quantum physicist, I would, first of all, advise you to read a lot of the science books out there. When I was a kid, there were almost no science books at all about the quantum theory, but now there are quite a few good ones, including my own. And so read up. Listen, watch the science shows on the Discovery Channel, on History Channel, National Geographic. A lot of good shows about the astronomy, about the universe, about Einstein's theories, all of it animated on television. So the first thing is keep up with popular science by reading magazine articles, by reading books, and by watching the TV. But hey, you can only go so far reading popular books. You have to settle down and learn it. And that means that in college, I would start to take mathematics and physics courses. Now, one question that I sometimes get is, do you have to be a genius in math to become a physicist? And the answer is no. However, you do have to be competent. That is, you have to master calculus. First year calculus, of course, is essential. Second year calculus, if you can hack it. But you have to pay your dues. And once you graduate, then there are a variety of jobs that you can apply for. And I'll summarize some of them after the break.
Does he know about string theory? He wrote the book on it. You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a quick question about how to become an entrepreneur as a quantum physicist. Well, first of all, there are many steps involved. And go to my website. I have an article entitled, So You Want to Become a Physicist. In fact, I remember when I was in elementary school, in fact, when I was in 5th grade, we had these pamphlets about what you want to become when you grow up. And one of the pamphlets had a very intriguing title, and that is, What do physicists and baseball players have in common? And I thought, ooh, gee, this sounds interesting. So I picked up the brochure, What do baseball players and physicists have in common? And I found out that they both get paid to do what they love. Baseball players get paid a lot of money to do what they love. Physicists, well, we don't get paid as much, but we do get paid to do what we love, which is quantum physics. And that's the link. And I thought to myself, hey, how can you beat that? How can you beat that? Getting paid to do what you love. And so like I said before, A, start to read about science, watch science programs. B, in college, well, take physics courses, but you have to take math. Not advanced calculus so much, but at least you have to have about a year's worth of calculus. And then once you graduate, there are 3 possibilities. One possibility is to work for the government. You can work for the National Bureau of Standards, which has a new name now, or you can work in private industry. That's where the money is. I mean, after all, Hewlett-Packard, the Varian brothers, many of the biggest names in high tech came out first as physics and electrical engineering majors and then went into business. And third, you can go into academia, which is what I did, because then if you're tenured, you can pretty much do whatever you want and get paid to do it. What's there not to love about that? Now, if you want to become an entrepreneur, there's a whole nother dynamic involved. First of all, you have to be content to, well, fail. Failure is one of the byproducts of being an entrepreneur. You're not going to make it big on the first try. Nobody ever does. But you have to have, well, you have to have money to back your ideas. The Hewlett-Packard, for example, went door to door in suburban Palo Alto, where I grew up, asking for people to invest in their garage electronics factory. That's right. They had a little electronics factory in their garage, and they went door to door asking people to invest. That's how Steve Jobs did it. That's how Apple computers got started. That's what the Varian brothers did in their garage. They would go door to door trying to line up investors. Now, today, of course, if you're sitting on a hot piece of software or hardware, you don't necessarily have to go door to door and advertise your garage equipment. However, that's one way to do it. Okay, well, let's take the next listener phone call.
My question is, why does observation collapse quantum wave function?
Well, you ask a question which goes to the very heart of quantum mechanics, and that is, if matter is a wave and it vibrates, and these vibrations talk about different possibilities, then how does the wave collapse to give you reality? Reality doesn't look wave-like. We don't see the fuzziness and the waveness when we actually look at the electron. We know the electron is here, right there at that exact moment. And so the wave function had to collapse. And this has been a source of consternation and debate for the last 80 years. For 80 years, the giants of physics, Einstein, Niels Bohr, Schrödinger, debated what does it mean when the transition is made between the wave-like properties of the subatomic world, which we can measure, and the fact that, well, electrons do seem to be like little steel balls. Where is the wave-like property? Well, if you look at a quantum mechanics textbook, it simply says, as you pointed out, that the wave collapses. Now, people didn't like that. For 80 years, people didn't like that. But what can you do? Quantum mechanics is a cookbook. It's a recipe book. It gives you the right answer every time you scatter electrons, protons, pi mesons, Higgs boson. Every time you scatter subatomic particles off each other, quantum mechanics comes out exactly right. Well, there are several ways of resolving this paradox. I'll tell you my way. One way is that, well, these waves represent different universes. And therefore, when you make a measurement, the universe decides to be in this universe versus another. In other words, there is a fork in the road. And before you hit the fork in the road, you can be in all different possible states, but after you make a measurement, you are in one state and not in a wave-like state. This is the many worlds theory. It's very controversial, but hey, most of my friends, many of the Nobel laureates, believe in the many worlds theory, which says that there are an infinite number of parallel universes. That when you make a decision, the universe splits into an infinite number of possible universes. So in one universe, you're listening to my radio show. In another universe, you decided to go out and get a hamburger, and you're not listening to my radio show. In another universe, you married somebody else. In another radio show, you went to a different college, chose a different career. Can you rule this out? And the answer is no, because electrons make a decision the same way that you make a decision. And again, this is a philosophical debate that's been raging for 80 years, and we're not going to be able to resolve it in the next 5 seconds, but get a copy of my book, Parallel Worlds, and in that book we go through the ins and outs of one of the greatest questions in quantum mechanics, and that is, can an electron be two places at the same time? Are there multiple universes? Find out.
You're listening to Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour, we're going to throw the lines open because this is your hour. Okay, well, without further ado, let's get right to the telephones. Let's take the first listener phone call.
I received your show at WDNG 1600. I want feedback on the theory saying that the moon is only the reflection of the Earth cast into the air. We have no gravity because these are just rays. These are something. The sun fuels off all the combustibles that are fed by the bodies on Earth. I need your feedback.
Well, I think from what you're saying, you have the idea that perhaps the moon is an illusion, that perhaps it's an illusion caused by the reflection of the Earth into outer space. I think that's what you're getting at. But let me say, first of all, that we have Newton's laws of motion, by which we can calculate precisely the forces between Mars, Jupiter, Saturn, and things like this. And that's how we send space probes. We can send a space probe right through the rings of Saturn. That's how accurate Isaac Newton's laws of motion are. And Isaac Newton's laws of motion says that the moon is real, that it does in fact revolve around the Earth, and the Earth in turn revolves around the sun. And that basic picture allows you to predict the motion of the Earth and the planets thousands, even millions of years into the future. In fact, Isaac Newton's laws of motion are some of the most precise laws that held sway for 300 years before Einstein came along and told us we have to make corrections as we go toward the speed of light. So, in other words, the basic picture that you learn in high school is actually correct. The moon, the Earth, they all have a gravitational pull. And from that, you can actually calculate the mass of these objects. Or let me give you some examples. Some people say, well, how do we know how much the sun weighs or how much the Earth weighs? Well, Isaac Newton's laws of motion is a mathematical equation. In it contains the mass of the sun, the mass of the Earth, and the mass of the planets. So we can actually calculate the mass of the sun, believe it or not. Even though, of course, on the Earth, we can only weigh things measured in tons. Using Isaac Newton's laws of gravity, you can then calculate the mass of the sun itself. So that's incredible. That's how accurate these laws are. And it does allow us, in turn, to create a space program, to create the Internet system that can circle the entire planet, to create the GPS system. All of that complements of Isaac Newton's laws of gravity. Okay, well, moving right along, let's take the next listener phone call.
Hello, Doctor. My name is Darren. I'm from Hamilton, Montana. I listen to you on, I believe, KGDO radio in Hamilton. My question is, after listening to a question of the actual tilt of the axis of the Earth, I would like you to explain the catastrophic effect if that axis actually did change, as this lady possibly was referring to. Thank you very much for your time. I love your show.
Well, thank you. And yes, we had a previous caller on another day who was hinting about the catastrophic effects of what happens if the tilt of the Earth were to change. So let me first explain. First of all, we have not one but two kinds of north poles and south poles. We have the magnetic north and also the geologic north. Now, the magnetic north does shift. We know that for sure because we can simply look at, for example, lava flows that solidified millions of years ago. By looking, for example, at lava flows in Hawaii, as a simple example, and then simply calculating the direction of the North Pole that was frozen as the lava began to cool and eventually freeze, we begin to realize that, yes, the magnetic north has shifted dramatically over the centuries and millennia. And then the question is, what about the geologic North Pole and the geologic axis of the Earth? If that were to change, we'd be in big trouble. I mean, really big trouble. First of all, the North Pole points in the direction of Polaris. Polaris is, as any Boy Scout or Girl Scout knows, the North Star. And we know that the axis of the Earth is very stable, except for some slight perturbations. Now, these slight wobblings of the axis of the Earth can be precisely measured. And if you correlate them with other cycles of the Earth, for example, ice ages, you find a good correlation. And so it is widely believed, though we can't prove it for sure, but it's widely believed by most physicists and geologists that the reason why we had an ice age, in fact, a series of ice ages, is because of the accumulation of the tiny wobblings of the Earth. So the axis of the Earth does tilt 23 degrees with respect to the plane of the solar system, but there are tiny perturbations which in turn can be associated with ice ages. And so we do know these things happen. Now, if an ice age were to take place just on the basis of infinitesimal wanderings of the axis of the Earth, you can imagine what would happen if the Earth really tilted. In fact, I just did an interview with the History Channel, a program called The End, that is the end of the Earth, which will be broadcast perhaps in fall. And there we asked that question, what happens if a black hole were to come by and the Earth's axis were to tilt? What would happen? It would be catastrophic. First of all, the crust of the Earth would begin to break apart. We know the crustal lines where the different fault lines merge, and they would be the first to begin to break apart as the crust of the Earth began to break apart. There'd be volcanic eruptions all over the Earth if you were to change the axis of the Earth. And even the oceans, much of the oceans would be flung into outer space because of the enormous shift in the tilt of the Earth. Then the question is, has it happened in the past? And we think that it might have happened for smaller objects such as the moon. It turns out that the moon helps to stabilize the Earth's orbit. If you use Isaac Newton's laws of motion and simply run the videotape forward millions of years into the future, you can see that if the Earth had no moon, the Earth would begin to wobble. And the wobble would then begin to get larger and larger until eventually the Earth would probably flip over. Now, that would be catastrophic, of course, and we think that actually happened to perhaps Mars. Mars has two small moons, too small to stabilize the tilt and the spin of Mars. So we actually do believe that Mars actually flipped over billions of years ago. So just to summarize, if the axis of the Earth really were to shift dramatically, it would be catastrophic. The Earth would experience all sorts of catastrophic changes in the crust of the Earth with volcanoes, earthquakes, and other kinds of disruptions. And we think that it might have actually happened in the past for Mars. The Earth, luckily, has a large moon. And the effect of the gravity on the moon is to stabilize the Earth's orbit. So we can actually thank the moon for preventing this scenario, which we think actually did happen to Mars billions of years ago. Okay, well, let's take a short commercial break.
This is Science Fantastic. The most up-to-date announcements and analysis from today's technological leaders every week on Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, this is your hour. Okay, well, moving right along now, let's take the next listener phone call.
I'm just wondering how close we are to discovering the fourth dimension.
Well, you ask a very interesting question. In high school, we learned that the universe has 3 dimensions, length, width, and height. And anyone who talks about a 4th dimension is considered crazy, a crackpot. And there are a lot of science fiction movies and stories about people and demons and whatever that live in a higher dimension. But all these theories and speculations never got anywhere. Because, of course, the bottom line is you have to have a physics experiment to verify any of these cockamamie ideas. Well, these ideas are now taken very seriously, though we cannot yet conclusively proven. First of all, we have something called string theory, which we think is the fabled unified field theory. That is the theory of everything that allows us to explain all the different forces of the universe. String theory explains light, it explains gravity, it explains the nuclear force. And this is the theory that, in fact, eluded Einstein for the last 30 years of his life. A theory of everything. Now, you may say to yourself, well, hey, that's nice. If it really is a theory of everything, how come you guys don't win the Nobel Prize? Huh? Well, there's a problem. There's always a problem. And that is that string theory, even though it's fantastic, seems to be the theory of everything that can explain light and gravity. It has a problem, and that is it predicts that the universe was originally born in 11 dimensions. 11 dimensions, not just 4, not just 10, but 11 dimensions. And then you may say to yourself, well, that's nice, but how do you prove it? How do you prove that the universe has a higher dimension? Well, believe it or not, we can actually prove this conjecture, no matter how preposterous it may seem. First of all, we do know that gravity spreads out by the inverse square law. If you were to double your distance from the sun, for example, the strength of gravity goes down by a factor of 4. That's the inverse square law. Why is it the inverse square? Because that's the surface area of a sphere. Gravity spreads out through all space and is diluted by the fact that spheres have an area which goes as the square of the radius. So that's why we live in 3 dimensions. We can prove that we live in 3 dimensions because light and gravity spread out as the inverse square. If it's spread out as the inverse cube, the inverse quartic, the inverse quintic, then gravity would drop much faster than expected, and that's what we believe would happen if the universe had a higher dimension. So that's one way of proving it. Another way of proving it is to go back to the beginning of the universe itself. As you know, gravity waves were detected, tremendous headlines as we detected gravity waves coming from the collision of 2 black holes 1 billion light years from the planet Earth. However, the question is, even though we have evidence of gravity waves, what is the largest source of gravity waves? Well, the largest source of gravity waves, we think, is the Big Bang itself. Not just the collision of 2 black holes in outer space, but the Big Bang itself, the creation of the universe. Well, given the fact that the creation of the universe also emitted so much gravitational radiation, it should be detected by gravity wave detectors. The next generation of gravity wave detectors will be in outer space. That's right, outer space. We want to have gravity wave detectors that are so powerful they can pick up radiation from the instant of creation itself using satellites in deep space. In fact, the European Union and the United States government, NASA, both of them are planning to shoot gigantic space-based gravity wave detectors into outer space. And once we loft them into outer space, perhaps we'll have baby pictures of the instant of creation. And once we have baby pictures of the instant of creation, we'll be able to see where the universe itself came from. And string theory predicts that the universe itself came from 11-dimensional hyperspace. In fact, if you saw the movie Interstellar, starring Matthew McConaughey, it was science fiction, of course, but at the end of the movie, Matthew McConaughey is hovering above us in another dimension. And so the movie Interstellar actually ends on string theory, because string theory does predict that there are higher dimensions, in fact, other universes.
Science Fantastic with Professor Michio Kaku. Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, this hour is your hour. Okay, well, moving right along now, let's take the next listener phone call.
Wow, first of all, it's amazing to hear your voice, Dr. Kaku. I have pretty much all of your books. I was really just calling because I was curious about the show in general, what time it's at and how to listen to it and whatnot. But I don't know. Here's a question for you that I haven't found the answer to, and I don't think anybody on the planet can answer. But I'm pretty sure you could, if anybody. What is energy at its rawest form? What is energy? I know it ties in with superstring theory and everything, but I'm really interested in this, and yeah, I don't know. You're the one person that I'd really like to get a response from. But yeah, I don't know. That's it. Again, it was pretty amazing to hear your voice. I have probably a book full of questions that I could ask a person like you. Like I said, I've read all your books and everything, and I'd like to make my own breakthrough someday. And yep, thanks again.
Well, thank you for the kind comments. And you want to know what energy is? Well, of course, if we did know what energy is, it would unlock some of the greatest secrets of the universe. However, in its simplest form, we define energy as simply the ability to do work. That is, the ability to move things. So energy is the quantity that allows us to move objects, okay? That's how we define energy. Mathematically speaking, is the force times the distance over which the force acts. That's the definition of energy. But the astonishing thing is that energy occurs in more than one form. In fact, it occurs in a variety of forms. First of all, we have the energy of motion, which gives us heat. Sometimes people ask, what is heat energy anyway? Heat energy is the energy of atoms in motion. That's all heat is. And then the other question is, well, what about light energy? That seems mysterious. What about gravitational energy? And how many different forms of energy are there? Well, there's light energy, there's gravitational energy, and there's nuclear energy. In fact, two types of nuclear energy, the weak force and the strong force. And as far as we can tell, that's it. There are just four fundamental forces. So what's all the problem? What is all the fuss about? The fuss is that these four forces, the force of light, gravity, and the two nuclear forces, don't like each other. They are expressed by different equations, by different physical principles. They don't seem to have anything related to each other. That is, what does light have to do with gravity having to do with the nuclear force? That's one of the greatest problems facing physics today. Well, of course, we've made progress on this question in terms of the light. we now know that that light force can combine with some of the weak nuclear force, giving us the electroweak interaction. So the nuclear force begins to combine with the energy of light, but gravity seems to be the difficult one. In other words, a unified field theory that eluded Einstein for the last 30 years of life would unite all four of these forces into a single theory. Now, the leading theory for all of this is string theory. String theory unifies all of them by saying that they're nothing but different forms of music. That is, if I have A, B, C, D, they're not anything fundamental. There's nothing fundamental about C sharp or B flat. They're just musical notes on a single object, the string. So the string unifies many, many different kinds of subatomic particles, of which we have cataloged hundreds, thousands of these subatomic particles. And so now we believe that string theory can also summarize the basic forces as well. And so now we have a very simple way of explaining not just force, but matter as well. That is the theory of everything. Then you ask the question, well, where does string theory come from? Well, at that point, I'm going to have to say we don't know. We just know that the theory seems to be the theory of everything. But where did it come from? Why strings? That's what I'm working on now, trying to figure out the origin of string theory. Well, let's take a short commercial break.
This is Science Fantastic. Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. This is the chance for you to get on national radio to ask that question that you've always been wanting to ask about science in this great universe of ours. Okay, well, let's move right along and take the next listener phone call.
I personally think that robots could free people with automation. What's your thoughts on the Venus Project and the guaranteed income?
Okay, well, I think you actually asked three questions. One about automatons, that is robots, and then the Venus Project, and then a guaranteed income. So let's try to break them down one by one. First of all, we've been brainwashed by Hollywood to thinking that robots are around the corner. Robots are quite primitive. They can barely recognize objects in a room. They're basically adding machines, and we forget that. So don't think that a robot is going to take your job anytime soon. But every year, we do make them smarter and smarter. Will they replace us? Maybe, but not for many a decade, perhaps late in the 21st century. Perhaps we may have robots perhaps as smart as a dog or a cat, maybe as smart as a monkey. And of course, at that point, we should put a chip in their brain to shut them off if they have murderous thoughts. And so robots do give us the possibility of saving on labor, repetitive labor. These are jobs that are dirty, dangerous, and dull, the 3 Ds. That's where robotics, I think, could have a very big impact on our economy. Jobs that are dirty, dangerous, or dull are jobs that machines can do very well. So why not let them do that? But this means that the job market will change. I mean, after all, we don't have blacksmiths anymore. We don't have wagon makers anymore, but no one cries about it either. But if you want to know what jobs are going to be phased out and what jobs are going to be opened up, then, well, get a copy of my latest book, Physics of the Future, where I have a whole chapter concerning what the future of robots is and how they will change the marketplace. Surprisingly, a whole array of new jobs will open up. But jobs that are repetitive will gradually be phased out.
Science Fantastic with Professor Michio Kaku. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open, and it's open mic in this hour. Well, before the break, we had a call, and he was talking not just about the future of robots, which I think is very bright. However, I don't think they're going to replace all human labor anytime soon. But he also asked a question about the Venus Project and about a guaranteed income. Well, those are pretty heavy topics, but these are basically utopian topics. The Venus Project and other projects are pushed by so-called free-thinking gurus who want to eliminate all capitalist, socialist, communist instincts and create a paradise on the earth. Well, it's been tried. In fact, the United States of America, our own backyard, was in part colonized by people from Europe who tried to create utopia. Unfortunately, it didn't quite work. All the early settlements eventually fell apart because of one basic thing: scarcity. As long as you have scarcity, you're going to have, well, people fight over these scarcities. And no matter how good the intentions are to create a utopian society, sooner or later, these scarcities catch up to you and bickering starts and people begin to fight over limited resources. But then the question is, if you fast forward it, we're not talking about America of the 1800s with the Shakers and the Quakers and other utopians. We're not talking about robots that perhaps can give us a guaranteed income. Well, at that point, all bets are off. If you look at Star Trek, for example, they have something called the replicator. You ask for it, and it comes to you. And then the question is this like a guaranteed income? Because if you want something, you simply ask for it, and the replicator creates it. So in other words, the replicator is quite a subversive instrument because it forces us to challenge all our conceptions of capitalism, socialism, and communism if you can get whatever you want by simply asking it. Well, we physicists have tried to look into this. This is called the molecular assembler. It takes raw materials, cuts up the raw materials, and molecule for molecule creates a new form of value. So starting with nothing, all of a sudden we can have anything you want. Well, Mother Nature actually has created a molecular assembler of sorts that can cut DNA, cut proteins, and reshape them. And it's called the ribosome. A ribosome is quite miraculous. It can take hamburgers, French fries, and in 9 months, just 9 months, create a baby. Absolutely amazing. In 9 months, Mother Nature can assemble molecule for molecule the pieces you get by shattering and digesting hamburgers and French fries and creating a baby. A human baby in just 9 months. Now, then the question is, can we humans do that? And the answer is obviously no. But is it even possible? Well, there's a debate about that. You see, at the molecular level, all sorts of new quantum effects start to come in, which kind of mess up all the well-laid plans of trying to weld and splice atoms together. It is really hard to do this. It took Mother Nature billions of years to get the machinery of reproduction off the ground, and we're far away from doing that. So to answer your question, I personally don't think that the Venus Project or other utopian projects will ever succeed because we have scarcity and people will fight over scarce goods. In the future, all bets are off, but then again, in Star Trek, they live in the 23rd and 24th century. So maybe by the 23rd century, we'll have replicators, guaranteed income, and perhaps at that point, all bets are off. I should also point out that one of my favorite episodes of Star Trek, the crew of the Enterprise finds a space capsule with the bodies of people who died in the 20th century, hoping to be revived by future people so that they can cure cancer, in fact, even cure death as we know it. So the crew of the Enterprise takes in these people, they're frozen, thaws them out, and 20th century people are now living in the 23rd and 24th centuries. One of them is a banker, and he asks the crew of the Enterprise, what century is this? And when they tell him that he's now been shot hundreds of years into the future, he says to himself, my investments, my stocks, my bonds, my assets, my money. I must be rich beyond imagination. So he tells the crew to put him in contact with his stockbroker, put him in contact with his banker, because he wants to find out how much money he has. Well, the crew of the Enterprise stare at him and say, money? What is that? We don't have money. We just learned about money in history books. We have replicators. We simply ask for things, and they're given to you. Well, as you can see, this is a very subversive concept. Okay, well, moving right along, let's take the next listener phone call.
Hey, I've been watching you for years now. I love you. Good job. This is Bill. I invented a spacecraft engine, and it will do over 160,000 miles per second. It doesn't use fuel. I don't have the patent on it yet, so I can't really describe it yet, but I do have a working model. I don't think anybody believes me, but I think that it will do over the speed of light, too. You know, Einstein's theory. All right. Thank you.
Well, thanks for the generous comments. However, I would have to say that nobody has been able to go faster than the speed of light. But, hey, if you have something, patent it first before you do anything else so that no one else can steal your idea. But personally, I think, well, you may have to go back to the drawing board. So far, Einstein has been proven right every time, and he says you cannot go faster than the speed of light. Okay, sorry about that, but once again, this is Science Fantastic with Professor Michio Kaku. Tune in every week as we discuss the cutting edge